And I guess you have to acknowledge that. I have to do that myself from my different computers. Okay, what I want to do first here is go to the text today. And I'm hoping that the light is such that we can actually see stuff here, okay? And maybe a little dim, but you have your own books, at least most of you, and you can follow along with the book if you don't want to read on the screen here. But we've been talking the other day about something called a cross product. It's going to be a very important thing for us, and you need to know how to compute one. What we use them for, the computation of them is relatively easy. On the other hand, the computation of them is also easy to make mistakes because you sort of get things backwards, or you multiply instead of adding, or add instead of multiplying, and so forth. And so you have to be careful. You have to be alert when you do this. But the cross product of three tuples called triples, and you can see them not right above my finger, but a little bit further above my hand. And what this is the three things you get, because you get a vector as an answer. And it may be hard to see here, but what it says is A sub 2, B sub 3 minus A sub 3, B sub 2. So in the way I remember this, you start out with 2, 3. A2, B3, and then you do the opposite for the first one. The second one is 3, 1 for AB, and the third is 1, 2. So I remember the first subscripts of the three as I go here, and I remember reverse them because there's a minus in each of them. That's one way to do it. Another way to do it is to think of it, if you know about 3x3 determinants, you can do a 3x3 determinant where you place, instead of A, B, and A1, 2, 3 here, you replace it with I, J, and K, which is not a real determinant, but you can act like it by putting the I where the A1 is, the J where the A2 is, and the K where the A3 is. Now, there is a subtle difference here, and that is, if you'll notice that in this one there is a minus. Now, when you use I, J, and K, these become three different things, not the sum or difference. It may look like a sum or difference, but it's actually adding a 3 tuple to a 3 tuple to a 3 tuple. And if you've learned the thing at the top, this kind of comes out backwards. This is like A1, I know it says B, but remember above it's A and B. This is like A1, B3, and up here it's A3B1, but notice with the minus in front, it comes out the same. So when you write it this way, you must put a minus in there. When you put it this way, at the top, the minus is automatically in there. And we can talk about that more later. But the cross product can be defined like this right here. Now, if I expand the matrix along the first row, that's what these things are, you would first have I times the determinant of this 2x2 thing below it. And I know you can't see it very well here, I guess, unless I take my hands away. Anyway, I'm hoping that this is not new to you. You did it last semester, or if you didn't, you can study it extra hard now. And what we did last semester, and what I'd like to do this semester, but I've already given you too many notes to read. If we just talk about matrices and determinants, if you interchange two rows of the matrix, in other words, instead of ABC rows, you make it BAC row. In other words, if I rewrite the matrix by interchanging the first and second rows, and you take the determinant of the result, you will get minus the determinant of the original one. That's one of the things you show if we do a little bit of matrix algebra. Okay. Now, what that means is, suppose I have a 3 by 3 matrix where I have two rows that are the same. Then if I interchange the two rows, you can't tell I changed, so the determinant is the same. But in general, the determinant of the first one is minus the determinant of the other one. So what does that mean? It means that if you have two rows that are the same, the determinant of the 3 by 3 matrix is 0. That's very important for what we will be doing. So one can study some matrix arithmetic and then do determinants. Right now, I'm just trying to do a 3 by 3 matrix so that you can actually check all these things directly instead of theoretically. But why are we interested in doing the cross product? Because of what's in the middle of the screen right now. The vector A cross B, the cross product, is orthogonal to both A and B. Okay. Now, the book proves it by actually going in, because it's 3 by 3, and actually computing what you get. And so this is a direct proof. It's kind of a blue collar proof where you go in and write down what the thing is and you do it. Now, if you notice, we have that this thing turns out to be 0. When the dot product of two vectors is 0, the two vectors are at right angles to each other, or perpendicular, or orthogonal. So the way he proves this is to take the dot product of these two things, and that's how he gets this. And this, by the way, is the determinant of, which we'll find out, if I have a matrix A, B, A, 3 rows, A, B, A, that's this determinant. And that's expanding it by the third row instead of the first row. In any event, what you want to remember and learn very well is when you take a cross product, you get a vector orthogonal to the two original. Now, if the two original vectors make a plane, if they are linearly independent, remember on Wednesday we talked about linear independence. If two vectors are linearly independent, you can think of that easily as thinking as they point in different directions and not the opposite directions. So if one points at a 30-degree angle, one points at a 100-degree angle, those are two linearly independent vectors in 2 space, 3 space, 5 space, it doesn't matter. Two linearly independent vectors form a vector space of 2 dimensions. They form a plane. So when you take two linearly independent vectors, and it doesn't matter how many dimensions, more than 2, 10 dimensions, 20 dimensions, whatever, the 2 dimensions, the 2 vectors, when you take the cross product, will give you a plane that passes through the origin, because we're thinking about these vectors of starting at the origin. Now, the vector A cross B will be perpendicular to the plane. It's called a normal vector. So it sort of sticks out at right angles from the plane. If you want to think about a plane and an arrow, the arrow sticks out of the plane at right angles. So the cross product gives us a normal vector to a plane formed by the first 2 vectors A and B. More than that, it turns out that if you know a point on the plane and you know this normal vector, you can get the equation of the plane. Okay? Now, before the book does that, the book brings up this idea we've already talked about, sort of, except what about this thing right here? This looks familiar, but actually it's different. A few pages back in the book, and a few pages back if you read my notes, there was a formula that said the absolute value of A dot B was the norm of A. The author just writes a single line. I like to write double lines. The norm of A times the norm of B times the cosine, hey, that says sine, the cosine of the angle. So the length of the dot product of two vectors. Now, that's a number. I'm sorry about that thing, not focusing. The absolute value of the dot product is the norm's product times the cosine of the angle between them. The norm, not absolute value, the norm of the cross product, because the cross product is a vector, the norm of the cross product is the length times the sine of the angle. So you need to learn those two facts because we use them. Okay. This also will give us the next thing the author talks about on the next page, which is that the area, and I hope this is readable to you, the length of the cross product, that's just what we just talked about, because the norm of the cross product is also the length of the vector, is equal to the area of the parallelogram determined by the two vectors. So when I write norm A times norm B times sine theta, I'm giving you the area of a parallelogram. So in the book, he computes a couple of parallelogram areas. Those are easy to do. I think you're capable of doing the computations by basically what you see in the middle of the screen there is you take the numbers and you put them in a matrix if you like, and you do a cross product, and that gives you a normal vector. You take the length of it by taking the square root of the sum of the squares, and you get the area of the parallelogram. Notice, once you know this, you don't need to know what the angle is. You just need to know the length and direction of the two vectors that make up the parallelogram. Okay, now there are also on the previous page, he has another important concept that I hope you've looked at because you've been doing notes and stuff. And apologize, don't know how to stop that. Two non-zero vectors are parallel if and only if their cross product is zero. Now again, we had something like that before. Two vectors are perpendicular if their dot product is zero. So some of the importance of dot and cross products is one of them talks about parallel and one of them talks about perpendicular. Those are two very important concepts in geometry. And that's all done here with cross products, and earlier with some of it was done with dot products. You need to know about the properties of cross products. And these are in the book are the properties. The number one basically says that we do not have commutativity. We have another term, it doesn't matter, but it's A cross B is minus B cross A. But you can multiply a scalar times a vector in any place or take it outside. That's number two, and you get the same answer. You can distribute the cross product over a sum both ways, and you can distribute the dot product. No, you can't distribute the dot product exactly the same way. Number 5 says the dot cross here is, interestingly enough, the same as cross dot. That's kind of interesting. Well, one thing you should notice here is they are in the same order. And then this turns out to be an important one, but we won't see that for a while. This is taking cross product and a cross product and changing it into dot products. you need to learn those rules. And there's one more, it's called a scalar triple product. In the book, it's just called a triple product. And that one turns out to be this A dot B cross C, which was number 5 up above that you can't see anymore. Number 5
And
was,
isn't that also the determinant of the 3x3 matrix?
I'm sorry?
Wouldn't the scalar triple product also be the determinant of the 3x3 matrix?
No. It's A dot B cross C, not A cross B cross C. It's different.
Yeah, but it'll return a scalar, which the determinant does.
Well, when A cross B cross C does not fit in one determinant, okay? If you take the A, B, and C and put them in rows and do a determinant, you get a dot product, not a cross product. It turns out you get a number, not a vector. When you take the cross product of a cross product, you get a vector.
Right. I think
you look at the answer up here, you get a number times a vector minus a number times another vector. So here you get a vector, but above it you get a number. Because it turns
right. I was talking about the scalar triple product.
Yeah. Down here. Okay.
Which isn't that the determinant of that matrix?
Yes.
That 3x3 matrix. Okay.
Yes, it is. It is. Right. I thought you were putting a cross here. If you're putting a dot here, that is definitely the determinant of the matrix where you put A, B, and C in that order. Now, if we go back and think about, I don't know if I answered your question, but I guess I didn't quite understand it. So maybe all that talk, you got the answer. I don't know. If not, we can talk about it later. If you turn rows of a matrix over, interchange them, every time you do an interchange, like if I interchange row 1 and row 3, I produce a minus on the matrix determinant, the matrix determinant, okay? So there are certain, if I interchange row 1 and row 2 and then interchange row 2 and row 3, I've made 2 changes in the determinant which make it back to the original. And that's why things like number 5 above that are off the page right now, that's why they're equal, okay? So if you look at number 5 again, if A dot B cross C is the determinant of the matrix where you have A is first row, B is second row, and C is third row, then what would this one be? Well, the definition below has the A, B, C, but it has a dot on the left-hand side. But the dot product, if I have C dot A cross B, that's the same as the dot product A, B, C. So this actually, if I write it out, is C dot A cross B. So that would put C first, A second, and B third in the matrix of which I wanted to determine it. And if you look into that, you'll see that you've made 2 interchanges, which mean the determinant's equal. So by playing around with a scalar triple product, you can do things when you are doing dot products. And anyway, there's also the concept of torque, which I don't really want to talk about at this moment. It's in the book. Basically, we talked about work as being a dot product. It turns out that the concept of torque, which has to do with twisting, that's a cross product. So you can read that. And I want to keep going here because we got other things I want to do today. We have already talked about equations of lines. And the book talks about that in section 5, but we already discussed it in the notes we had. And basically the formula, and I hope that we can make all this readable. If I have a setup where I have a point and I have a vector that tells me what direction I have. Now, directions are length 1. But I can talk about being in the same direction as by having a vector of length 2 or 5 or 7. And as far as a line goes, I have a line if I add multiples of a direction or a vector in the direction of a direction, that's TV. It doesn't matter what the V is as long as I pick any two things in the same direction. But it would change what the T is. So we can model motion and speed by changing the V and making the V longer. When you make the V longer, it turns out to be able to talk about things moving faster. We'll be talking about that later. But this R over here is a cover for X, Y, Z, or in 2 dimensions for X, Y. So what this is a vector equation, which is 2 scalar equations. And so the author, a little bit further down, writes the scalar, in this case 3. So these 3 equations are extracted from the one vector equation. And I think you know about lines already, okay? So I don't want to dwell on lines at the moment because I think we've already talked about them. On the other hand, we haven't talked much about planes yet. And so I want to talk about that a second. It's in section 5. Again, this is all supposed to be review for you. But, and I'm going to work on trying to make a lighting situation that's better than this. I don't think this is up to my standards. Anyway, what this equation here says is, if I have a point, which is called r sub 0, that's a vector, the set of all points on a plane can be determined if, in addition to the point, I know a normal vector. The normal vector in this equation is called n. R, remember, is x, y, z. So I don't know why he likes R. I don't like R, but it's okay. N dot x, y, z minus r naught is 0. The dot product with this is 0. Now, if the r is 0, this passes through the origin. If the r naught is not 0, it doesn't. And you can write it this way because dot products are distributive and so forth over subtraction. And he writes it out this way. This is what we call the scalar equation. I just call it the equation of a plane. The A, B, and C is the normal vector n, and the x naught, y naught, and z naught is the point. So if you know a point and a normal vector, this is the equation. What does the book do a lot? Find the equation of a plane through the point with normal vector so-and-so. Now, in the equation up here, there are 9 letters. When you get the equation done, there should still be 3 letters, x, y, and z. To get rid of 6 things, you need to have 6 numbers. And in this problem, he provides you the 6 numbers to stick in to the formula. So if you know the formula, this becomes what I call a very easy problem. Okay? Now, one comment that the author makes, he calls this equation linear. I do not. I call it affine, A-F-F-I-N-E, unless the D is 0. Linear to mathematicians means that the thing passes through 0. If I put 0 in for x, y, z here, I do not get 0. I get minus D. But in elementary sort of stuff, anything that's line-like or plane-like or flat, sometimes people like to call linear. And I do that too, but it's not the definition that we will be using later. We're going to be talking about linear functions, and we have to understand that things that are linear go through 0. We'll get to that. Anyway, there are, in the exercises in the book, lots of trying to find equations of planes. And what I would recommend to you, and we can talk about it Monday, I think you should try to do these problems, okay, about planes from 23 to 40, or similar problems in WebAssign. Okay, this is in section 5, and there are more of them. On the next page, there are more problems to do. Find an equation of a plane, and these are a little more challenging on the next page because they aren't like that cookbook problem I told you a minute ago with 9 letters to figure out, and they give you 6 numbers. If you know the formula, that's easy. Some of the ones on the previous page to this one are just that easy, and then they get a little more difficult, but they ought to provide you with enough information to sooner or later get a normal vector and a point. Suppose we have 3 points. We don't have a normal vector, we got 3 points. So we are point rich and we are normal vector poor. Okay, what we'd like to have is a point and a normal vector. We got too many points. What do? You take one of the points and subtract it from the other 2, making 2 new vectors. What you're actually doing is finding the names of 2 vectors that are going to give us a normal vector. So you should take one of the 3 vectors, subtract it from the other 2, producing 2 new vectors. Take the cross product of those 2 vectors, and that is the normal vector. Now, I just had a wonder here. I'm going to stop to share a second. Are we recording? Yes, we are. Okay. My other computer didn't act like I was recording. Okay. Has anybody got any questions about that kind of stuff? I'm going to go back to the screen share, but how are we doing on reviewing the cross product and equations of lines and planes? We'll be using them a lot. Nobody's talking. So if you haven't looked at section 6 yet, please do so. And when you do so, you will see lots of nice pictures. The things that are pictured on the right now are called cylinders. Cylinders are defined on page 874. And they may or may not look like cylinders that we normally have, because we normally think of cylinders like these pages I have that you can see on the right, but this is also a cylinder by the definition. Okay, now over on the other page, we have something else. It's called quadric, Q-U-A-D-R-I-C. And that is one of the things you can get if you have an equation in 3 variables, which is second order, ax squared, by squared, and so on. Now, if I just had 2 of those instead of 3, I would have what are called conic sections: parabola, hyperbola, ellipse, circle, so forth. If I have 3 letters, A, X, Y, Z, in 3 dimensions, I get what are called quadric surfaces, like that egg we saw a minute ago. Now, if you haven't looked in this section yet, all of a sudden, it gets you nice, pretty pictures in color and so on. And the author is trying to show you the graphs of these things, what they look like. These things on the bottom are called saddles. Sometimes English saddles, actually, because there's no saddle horn, but it's also a hyperbolic paraboloid. And that's because it's a kind of a combination of a parabola and a hyperbola. So, thousands of years ago, these things were named. what you look like at the top here, if you've traveled around the country, around the world sometimes, this is like an atomic reactor, okay? And these other pictures are nice pictures, and they give you examples of equations. And the next page gives you nice pictures and so on. Now, what we're going to do in our class is refer to these occasionally. I am not going to test you over which equation gives you an ellipsoid, or which equation gives you a hyperbolic paraboloid, or those kind of things. I'm hoping that you'll look in the section, study it, try to learn some of the formulas and which pictures they give you, but I'm not going to test you over that, because that's the kind of stuff you can pick up at any time when you need to. And so I hope that's understandable. So I'm not going to be testing you over section 6 when we deal with these things, but I want you to know about them. So please look at them. They're nice pictures. There's also lots of stuff online that you can go and learn what things look like that way. Lots of different stuff you can do that way. So, okay. Now, what we're now going to do, or I hope we're going to do, is start the rest of the class, which is where we're supposed to start, begin with. However, if you look into chapter 13, it's about a study of certain kinds of functions. If you look in chapter 14, it's a study of certain kinds of functions. Now, I am going to present you some stuff at the beginning of these things which work for both chapters instead of separately learning each. So we're going to be in chapter 13 and chapter 14 in part at the same time because of what I wish to do. So I'm going to change the screen now and show you something you haven't seen, or maybe. When I say that, did any of you get an email today about more notes? On Blackboard, I put an information that says you have a new set of notes. The new set of notes is what you see right here. So I see Peyton says yes. Okay, good. Anyway,
Yeah, I saw him too.
I put this on this morning. Okay. So let's sort of look at, you probably haven't had a chance to look at it. So let's look at my nomenclature, so-called. Okay. So I say in calculus 1, just sort of reading it. I don't like to read to you, but anyway, you need to be able to read. So if you can't, maybe I can help you. In calculus 1, real valued functions of a real variable were considered with respect to continuity. These were functions f that had both a domain df and a range rf that were subsets of the real numbers. So when you hear real valued function, that's what the values are. That's what the f of x's are. And if you then hear of a real variable, that tells you what the x's are. So the first half of that sentence tells you what the y values are. The second half tells you what the x values are. Now, not literally what they are, but what kind of thing they are. So, as I said below that, you can read it. The graph of such a function is usually depicted as a set of ordered pairs in the plane, and that's what you might call high school. Okay. When the domain is a subset of n dimensions. Now, in the book, the author stays with 2 and 3, but there's no real reason to stay with those. You can have 5.
Excuse me, Dr. Brady.
Yes, sir.
I hate to interrupt, but Keegan texted us to tell you that his computer hard drive gave out, so he's trying to fix his computer currently.
Okay. And all of you know, and you can tell Keegan back if you wish, he can get on his cell phone and get into the same class if he has the app, the Zoom.
Okay.
So if it fails you for anybody, you can get a small version of this and at least get the audio and a small version of this on your phone.
Okay.
If you tell him, I understand, and you know, I hope he can get back soon. Okay.
Okay. Apologies for interrupting.
Yeah, no problem. Okay, I'm just looking to see. I secretly took your guy's picture a while ago, and he's not on it. So I'll need to add him in for being here. Anyway, to get back to what I was saying, if the domain is a subset of real numbers and the range is multidimensional, I think I skipped something here. Let me go back. If the domain is 10 dimensions and the range is real, then we have a real valued function of a vector variable. The domain is vectors, the range is real. For example, the norm of a vector is a number. That's a real valued function. Okay, next little paragraph. When the domain is a subset of real numbers and the range is a subset of m dimensions, it's called a vector valued function of a real variable. So I think you get the point. Okay. Now, the author, when the author says a vector valued function, he stops with that. And he means of a real variable, but it doesn't tell you. When some of the first lines in chapter 13, he says, we're going to talk about vector valued functions, and he stops the sentence. He should say of what, because you can have vector valued functions of a real variable or a complex variable or an n-dimensional variable. There's all kinds of different things we can do. And so I'm trying to show you here, when you say something with what the domain is, what the range is, it helps people understand how we're going to picture it, or at least conceive of it. So down here, definition, notation. When I have an n-dimensional domain and an m-dimensional range, so suppose we're going from 4 dimensions to 7, suppose. And f is a function. Now, functions relate to sets. What they are pairs of things, and up till now, the pairs have been real numbers. So when you put together 2 real numbers, you get a pair of real numbers. If I was trying to graph the thing from 4 dimensions to 7, I would have 11 things in my picture, 11 dimensions, because if you stick the domain and range together, 7 and 4 is 11. We can't picture that. So we have to deal with other ways, which we'll be discussing. In any event, when I go into more than one dimension, I try to always indicate that by heavy print in printing, or I put a bar under the F to tell myself that, so I don't confuse a vector valued function with a real valued function. Okay. Now, my domain is n dimensions, so you have a vector of n. The value is m dimensional, so the y is now an m vector. So I take n things and I transform them into m things. We call the y a vector, we call the x a vector, so it still looks the same, y is f of x, but it means something very different. Now, the good news is, however, that when I go into m dimensions, I can always explain it by having m functions go into 1 dimension. Now, so because of the subscripts for vectors, I'm going to use superscripts, not powers, superscripts for which function, because a function that goes into m dimensions like 7 is going to have 7 functions that go into 1 dimension. In other words, we can break up this function into 7 other kind of functions, each one of which is being real valued. Now, I'll get this done. If n is 2 or 3, we usually use x, y, and z instead of 1, 2, and 3. Or in case of 2 dimensions, we just usually use x, y. And these are the cases where we can think about graphing. Now, let me give you a general overview. When you go from one dimension to m dimensions, that's when we are studying curves. Last, in Calc 2, you studied parametric representations of curves a little bit. And that means the domain was a parameter t, and you had f of t was like two things or three things or four things. Like if I say for every t, I have cosine t, comma, sine t. In other words, I have an ordered pair. If you think about what that looks like, if I only graph the range, not the pair, just the range, I get a circle. So if I have vector valued functions of a real variable, that's when we study curves. And in the text, that's called chapter 13. Okay. If instead I study functions that have a vector domain and a real range, that's called chapter 14. We want to be able to talk about things from 2 dimensions to 1, 1 to 2, 2 to 5, 5 to 2, 5 to 1. We need to be able to have notations and function stuff for all of this. So what do we do with these functions that we are now going to study? So instead of studying chapter 13, where I'm talking about curves immediately, or instead of doing chapter 14, when I'm talking about certain other kinds of functions, I want to talk about them all at once in terms of limits and in terms of continuity, both of which you can do separately, but it makes no sense to do it separately if it's the same stuff, except occasionally you won't have a heavy L if L is real. If F is real valued, you'll have a F without heavy or without a line under it. If the domain is real numbers, the X won't be heavy font. If the range is real numbers, the L won't be heavy, and so on. Otherwise, it's pretty much the same. And to show you it's the same, you'll have this lovable thing you guys remember, I'm sure. What do we mean when we talk about limit? Now, I don't mean the formula we use, I mean the definition. And the definition of limit is an epsilon delta definition, which if you haven't grown to love yet, you will. Okay.
Hey, Dr. Brady,
Yes, sir.
on page 2, you have a superscript on the E. What is that in your exposition?
On page 2, this is where.
In your exposition section, you have a E representing your, what's that
this,
superscript?
This thing? Yes. That occurs when you mistakenly use round brackets instead of, in terms of LaTeX. LaTeX is trying to understand what I wrote. I should have put round brackets instead of curly brackets around the thing I was describing. I didn't see that. That will be corrected. So this should be 3 in the case we're talking about right now.
Okay, thank you.
Thank you. So you guys should tell me these things sometimes. I mean, I write an awful lot of stuff that you're going to find out. And these things sometimes escape me. I try not to do. I try to be as perfect as you'd ever meet anybody. But anyway, so you got me on a mistake. So that's going to be, if that was Brent, he's going to have a harder test. Okay. That's a joke. This is the epsilon delta definition. You need to learn it. It says for every epsilon, there's a delta, there's numbers such that if you take anything in a domain and it's a distance away from x naught, remember we're approaching x naught in the limit idea. If a distance is small, then f of x is close to L, and we measure that by saying this difference is small. So while this, I'm hoping that's like, oh yeah, I remember that. Okay, so this is what I mean by limit. Okay, and these can be vectors. F can be vector valued, L can be vector, or they can both be real, and so on. It's the same definition, the one you had in Calc 1. The only difference is we had a straight line here for absolute value and a straight line here for absolute value. If I have a vector variable and a function that goes into reals, then this will be a straight line for absolute value. if I have real numbers going into vectors, this will be straight lines and this will be vectors. It's all one definition. I see no reason to have 2 or 3 different chapters and have to introduce it every time. Okay, that's why I'm doing this way. So I know we're running out of time. It's 21 after already. What's in these notes that you haven't had a chance to see yet? What's the limit of a constant function? You know that already, but we don't know it for this kind of generality. What's identity function? And that norm is new. If you have limits, they're unique. What's the limit of a constant times a function? And you know what it is constant times a limit. Okay, it's the same as in real numbers, but you have to verify it all here. What's the limit of the sum of functions? What's the limit of the difference of functions? What's the limit of the product? Well, I first do a couple of things about boundedness because of products, but what's the limit of the product of functions? Oh, now we got a problem. How do you make the product of vectors? See, we don't have the product of vectors. But if one of them is real and the other one is vector valued, then we can multiply them together. And the limit of the product is the product of vectors. Notice when you get to this number 12, this will be heavy print, but this won't be. This will be heavy font, but this won't be because this one's real valued and this one's vector valued. And you see up here, I have a real valued function times a vector valued function, because when you evaluate it, you get a real number times a vector. That makes sense. And it turns out it's okay when you do it that way. But we'll never see vector. You won't see heavy print here unless I make a mistake, because it doesn't make any sense. Anyway, so I'm just showing you sort of what's in here. And the latter part of this are some things that are nice. When I have this complicated thing, all it is N or M, things like you had in Calc 1. So we reduce everything in vectors down to everything you did in Calc 1. Therefore, you have 10 of them. You just do 10 things instead of one thing like you did in Calc 1, and so on. So please try to read through these notes. It's an attempt to settle for once and for all things about limits and continuity, no matter what these functions are. And I have found that that's the easiest way to make the rest of the material palatable. Now, I'm 23 after, I apologize. It would appear that we are going to be together in remote. Let me get rid of the